Super. Okay, so we're really delighted to have Neill Warrington back for the second of his two seminars. I am introducing Neill because, well, for reasons that we will not put onto YouTube, but we all know and understand. So as a brief bio, Neill Warrington is a theoretical nuclear physicist. He specializes in many-body physics and is currently a postdoc at MIT. Neill earned his PhD at the University of Maryland and went on to a postdoc at the Institute for Nuclear Theory in Seattle. And then for the non-physicists out there, itinerant since birth, he spent much of his childhood in Hawaii and Germany. And outside of physics, he writes songs and stories. So Neill, when you are ready, please take it away. We're excited to hear what you have to say.
Excellent. Cool. Thanks, Will. All right. So much like last time, so in making this talk, I was sort of vacillating between technical and non-technical. And so actually, I've made what I think is a pretty educational talk for the very experienced members of the audience. I hope this is not boring, but my aim was to make it educational rather than to overload you guys with results. So just to recap, I'm spending these 2 weeks talking about two topics: core collapse supernovae and dilute nuclear matter. We talked a lot about core collapse supernovae last time, and today we'll talk a bit more about core collapse supernovae, but then we'll work our way into dilute nuclear matter and what it has to do with the story. All right, let's just see. Just because I don't expect you to remember things spanning a week, I don't remember either. So here's a brief review of what we covered last time, in case you've forgotten or you weren't here. So basically, the first thing we covered the life cycle of a star. So we learned that stars are born in nebulae. Nebulae are giant clouds of dust in space, and hydrogen atoms, basically in interstellar space, clump together under the force of gravity and begin to form stars. And once a star gets sufficiently big, gravity causes the hydrogen atoms within a forming star to move fast enough that eventually this sparks the fusion process. And most of the life cycle of a star is spent undergoing fusion. Fusion is what supports the star. It's what keeps it buoyant against the force of gravity. And we learned that the basic fusion process is to take 4 protons or 4 hydrogen atoms with the electron stripped off and to fuse them into helium. This is a highly energetically releasing process, and the energy that comes out keeps the star buoyant. Now, as a star lives and ages, it makes heavier and heavier elements. The first step is to fuse hydrogen into helium, but then eventually fuel gets exhausted, and so the helium eventually gets formed into carbon. The carbon gets fused into oxygen. Oxygen gets fused into silicon, and this process terminates at iron. Specifically, it actually terminates at nickel-62. Nickel-62 is a hair more bound than iron, but just for the sake of simplicity, we'll call it iron. Basically, all that matters is that there's a most bound nucleus, and fusion stops at the most bound nucleus. You can't release energy after the most bound nucleus. So basically what happens as a star ages, it builds up a giant iron core, which grows. And what we spent some time last time deriving was that once this core of essentially degenerate matter exceeds something called the Chandrasekhar mass, it collapses because the force of gravity overcomes the degeneracy pressure, which is what kept this core afloat. And the collapse of the core initiates something called a core collapse supernovae. We'll talk about this picture a bit today. This is a picture of a particular supernova called supernova 1987A. It was seen in 1987, and it's the closest supernova that we have seen in a long time, and a lot of physics was gleaned by just looking at this thing. So we more or less, this brings us close to the end of last time. Then I zoomed in on the core collapse, and I argued that something called the neutrinosphere is an important piece of the puzzle. And we'll spend most of today talking about the neutrinosphere. This is a sort of a cartoon of what's happening at the center of a core collapse supernova. The iron core collapses and rebounds, and that rebound slams into matter, causing an initial ejection, and then neutrinos diffuse out of the newly born neutron star, which lies at the center of a supernova. So they bounce off of this very dense matter and eventually decouple from this dense nuclear matter at a layer called the neutrinosphere. The neutrinosphere sets the spectrum of energy of the neutrinos coming out, and then these neutrinos slam into the rest of the matter and cause the explosion to happen. So we're going to concentrate on this part of the story today. The neutrinosphere, Why is it important? Stuff like that. Here's roughly the story. So first off, you might be wondering, why the heck are neutrinos important? You know, there's a lot of different types of particles participating in processes here. There's certainly light coming out. Why are neutrinos particularly important? So I'll first explain why this is. Once we understand that neutrinos are indeed an important part of the story, I'll go on to talk about the neutrinosphere. It's a gas of nucleons that are low density and warm on the scale of nuclear physics. Now, once we know that neutrinos propagating through the neutrinosphere are important, we'll delve into, okay, well, how do we actually solve the new physics of the neutrinosphere? This will take us into an interesting topic of what are the interactions between neutrinos and nucleons. And then finally, we'll use modern effective field theory methods and lattice field theory to solve, at least at leading order in the effective field theory expansion, the many-body physics of the neutrinosphere. So let's begin. Why the heck are neutrinos important? You can figure out that neutrinos are an important aspect of core collapse supernovae by staring very carefully at the data that comes off of supernova 1987A. So basically, this is a picture put together of the supernova by the Chandra X-ray Observatory. This is actually a superposition of light of a varying number of wavelengths. It takes a wide band to put together these details. But basically, I have a Mathematica notebook that does all the calculations I'm about to flash to you if you want to know them. But basically, okay, this supernova popped off about 170,000 light years away. Might sound pretty far, but on galactic scales, it's not terribly far. It was in the next galaxy over, and it's how we got a lot of information from it. And the first thing that happened after this supernova blew up was Kamiokande, which is a giant water-filled tank that is a neutrino detector, flashed. So what we're looking at here is basically the life of the detector. It's just sitting there, detecting neutrinos all the time. And over a 12-second window, Kamiokande, which are the yellow points, saw 12 neutrinos. It was a clear signal, something happened. In addition to Kamiokande, actually two other neutrino detectors, IMB and Baksan, also flashed, giving very clear evidence that some neutrino signal is passing through Earth. A couple hours later, a very bright light appeared in the sky, and this was the optical evidence that supernova 1987A had indeed happened. It was actually first seen in neutrinos. And the simple explanation for why that is that neutrinos only undergo the weak interaction. And so they're actually able to pass through matter much more easily than light, which undergoes electromagnetic interactions, which is much stronger. So the light is sort of stuck inside for a while and can only come out well after the neutrinos did. Now, okay, neutrinos can be produced inside the core. So the core collapse is a really energetic, violent process, basically. A bunch of really squished iron nuclei suddenly collapse. And there's many ways that neutrinos could be produced in this process. As we learned last time, an electron capture process can produce neutrinos. So a proton can combine with an electron to produce a neutron and neutrino. That neutrino escapes the star, escapes the center eventually, and hits Kamiokande. There's other ways too. Two neutrons, for example, can knock each other off shell and produce two neutrinos. These neutrinos can bleed out and eventually reach Kamiokande. There's an infinite number of reactions that I haven't written that can produce neutrinos. So there's microscopic mechanisms for neutrino production and clear evidence that they were made. Now, what's really cool is that you can take this data right here and trace and estimate how much energy was lost in the core collapse, how much energy was lost from neutrinos in the core collapse. And what we're going to find is that a large fraction of this energy must come out in neutrinos given this data. This is a fun exercise. I'm really excited to share this with you. So first off, how much energy is released roughly in a core collapse supernova? It's actually quite simple to estimate. Basically, the picture is this. You have an iron core of Chandrasekhar mass that starts off with a radius of 6,000 kilometers. It collapses to a much denser object with radius 50 kilometers. This text is probably too small to see, but this says 6,000, this says 50. Now, these numbers 6,000 and 50 take some time to deduce, but just take these as given, that the iron core starts out at 6,000 kilometers and collapses to a radius of 50 kilometers. It's very easy to calculate the energy released in this process. It's just the difference in the gravitational binding energy, which for a sphere of uniform density of mass m is given by this. Now, this is not a sphere of uniform density, but just for the sake of an estimate. So if you plug the numbers, initial radius, final radius, and the mass, what you find is that As a result of core collapse, around 10 to the 55 GeV is released. Now, this looks like a big number, and this is a big number, but the problem is it's like unimaginably big. And the issue with unimaginably big numbers is that they're hard to imagine. So I've tried to give you a little bit of context about just how much energy this is. So for example, 1 gallon of gas, if you burn 1 gallon of gas in your car, what you get out of it is about 10 to the 17 GeV of energy. Okay, that's like 38 orders of magnitude in between a gallon of gas and the energy released in a core collapse supernova. Okay, so 10 to the 38 gallons of gas, it's roughly 10 to the $38. That's a lot of gas. So that's not even sufficient to like gather how much energy this is. So I went one step bigger. So if you look up on the internet, the global energy consumption of all humans in the world in 1 year, according to some websites, it's roughly 10 to the 30 GeV. Suppose we take that at face value as true. Still, this is 25 orders of magnitude less than what comes out of a core collapse supernovae. The amount of energy that comes out of a core collapse supernovae could run the world for 10 to the 25 years. That is 100 Avogadro's numbers of years. That is so much energy. Okay, a lot of energy comes out of a core collapse supernova. Now we're about to deduce that most of it comes out as neutrinos. So here's the setup. This is a cartoon of what happened. So a supernova exploded 170,000 light years from Earth. A neutrino burst propagated out from that supernova and comes out as a burst of neutrinos shown in pink. Okay, so this is a 2D projection of a 3D process. And this neutrino burst passed through Earth. As this neutrino burst passed through Earth, they slammed into Kamiokande and IMB and Baksan and gave a signal. Now we can use this signal to estimate how many neutrinos pass through Earth, and then we can use that to calculate, well, how much energy was released in neutrinos. Like I said, I was trying to make this educational. I hope this isn't boring for you. So here's the idea. A neutrino beam, that's what I'm calling this burst of neutrinos that comes from the supernova. It's a beam of neutrinos. It has an unknown density of neutrinos. We know how energetic they are. They all have about, between 10 and 40 MeV of energy, but we don't know the density given this data yet. We can deduce it though. So the main goal of what I'm about to do is to figure out what's the density of neutrinos that pass through the Earth. If we know that, then we can deduce how much energy was in neutrinos. Well, it's actually not so hard to figure out. So basically, Kamiokande is a giant water detector. In the spherical Cal approximation, Kamiokande is a giant box full of many, many nucleons. It's about 3,000, I have my cheat sheet here, 3,000 metric tons of water. You can convert that into a certain number of nucleons, and we can deduce how many neutrinos pass through by just first looking at, okay, well, how many neutrinos can one nucleon scatter? Simple. The amount of neutrinos that one nucleon scatters is basically the volume that the nucleon sweeps out as the neutrino beam passes through it times the density of neutrinos. Basically, you can imagine this neutrino beam passes the nucleon carves out its cross section out of this beam, and that's how many neutrinos scatter. So that's over here, okay? The amount of volume that the nucleon carves out of this beam is its cross section. That's how big it appears to a neutrino. That's basically the area. And then the length that it sweeps out is the speed of the beam times the time extent of the beam. V here is the speed of light because neutrinos move at the speed of light approximately. And delta T is 12 seconds because if we go back, it's a 12-second signal. So the number scattered by one nucleon is the volume swept out by the nucleons times the density. We don't know the density, but we want it. Okay, Kamiokande is not one nucleon, though. It's many, many nucleons. And what we have is information about Kamiokande. So we can go from one nucleon to many nucleons approximately, simply. Well, the number scattered by all the nucleons is just the number scattered by one nucleon times the number of nucleons. This is a rough approximation, not accounting for interaction effects between nucleons, which will change the cross-section. But anyway, as a rough estimate. Okay, if you look up on the internet or just calculate it yourself, the low energy cross-section for neutrinos and nucleons is this. It's crazy small, 10 to the 48 meters squared, or 10 to the 40 minus 47 roughly. Anyways, it's energy dependent, c'est la vie. We know all numbers in here but rho v, okay? We know that the number scattered is like 12 neutrinos if we look back. We know the number of nucleons because the mass of Kamiokande is 3,000 tons. We know sigma, we know V, we know delta T. We solve for the density of neutrinos in this neutrino beam. You get like 2,000 per meter cubed. I think that's kind of crazy. Like just from a blip in a detector, you can deduce the density of a neutrino beam that comes from a supernova. All right, we're close. All right, it's one short step to deduce how much energy was released in neutrinos. The amount of energy is, well, the energy per neutrino. It's roughly 10 MeV if we go back to the data, times the number of neutrinos. The number of neutrinos is easy to figure out. It's the density of neutrinos times the volume of this neutrino beam. If you examine this wavefront going out, the volume of this thing is basically 4 pi r squared. Remember, this is a 2D projection of something that happens in 3D. So it's 4 pi r squared times the extent of the beam, which is V times delta T. We know every single one of these numbers. R is 170,000 light years. V is the speed of light. Delta T is 12 seconds. Rho V is 2,000 per meter cubed. What you get is roughly 5 times 10 to the 54 GeV. All right, compare this with our estimate of the gravitational binding energy release, which is 3 times 10 to the 55 GeV. We just got within 10%, okay? This very rough estimate would indicate that roughly 10% of the gravitational collapse energy comes out in the form of neutrinos. This is a rough estimate, though, that doesn't take into account for any losses in the detectors, any loss in energy along the way as it propagates through stellar medium, any loss of neutrinos as it comes out through the supernova matter. I'm not prepared to do this in front of you because it's hard, but a more sophisticated analysis gives that actually not 10%, but nearly 99% of the energy released in a supernova comes out in the form of neutrinos. This is why neutrinos are so important. Basically, all the energy comes out as neutrinos. Okay, so now that we know that neutrinos are important, let's review the neutrinosphere. And basically, what I'm going to try to do for the rest of the talk is slowly reduce this to a solvable nuclear physics problem. But there's some phenomenology that is fun to understand along the way. So just to review, the neutrinosphere is the layer inside the center of a core collapse supernovae where neutrinos begin to decouple from the dense nuclear matter that they're propagating through. Last time, I flashed some properties of the neutrinosphere to give you an idea of what this stuff is. It's basically a gas of nucleons and electrons. In the nucleon content, it's roughly 90% neutrons, 10% protons. It's neutron rich because of the electron capture process that happens as the star collapses. And for electric charge neutrality, there's an equal number of electrons and protons in the gas. So in terms of nucleons, it's basically all neutrons, but there's also protons and electrons around. It's roughly 3% of nuclear density. If you've not been exposed to the concept of nuclear density before, it's 0.16 per Fermi cube. This is the density of a lead nucleus, roughly. This is low on the scale of nuclear physics, and its temperature is like 5 MeV. I'm not an expert in heavy ion collisions, but I'm pretty sure this is kind of cold compared to a heavy ion collision. In spite of it being a relatively dilute and warm system, it's still strongly interacting, which makes understanding the neutrinosphere challenging. We deduced last time that the scattering length between neutrons, which is negative 18.9 Fermi, is a lot bigger than the interparticle spacing, which is on the order of 5 Fermi. Okay, so what this means is that to the neutrons in the medium, they look like this to each other. There are a bunch of overlapping spheres which are never not in contact. This is what makes the system strongly interacting, and this is what makes solving the neutrinosphere physics difficult. Now, how do we know these numbers? Because smarter people than me figured them out. In particular, Radice and company at Penn State do full 3D supernova simulations. These days, if you know about this community, getting to 3D is difficult, but now people really do, legit 3D simulations, and they just track the neutrinos and counted at what density in the first plot, temperature, and electron fraction, do they decouple from the matter? That tells us the properties of the neutrinosphere, and this is where I get the numbers that I just told you. So because the cross-section between neutrinos and nucleons is energy dependent, it depends on the energy of the neutrinos at what density and temperature they decouple. But roughly, if you translate this density plot and this temperature plot into a range of temperature and densities, when the neutrinos decouple, you basically get this. They decouple at a temperature between 2 and say 9 MeV, and at densities between 0 and 3% nuclear density. So if you want to understand neutrinos, you've got to solve low energy nuclear physics in this region right here. And by the way, this fraction of 90%, 10% that I keep telling you comes from examining the electron fraction of the neutrino decoupling. Good. Okay. Now, let me finally show you that the neutrinosphere is important. I keep saying this, but here's a proof. So what we're staring at here is our two core collapse supernova simulations. Going from left to right, this is the snapshots of the simulation happening, 180 milliseconds into the collapse, 250 milliseconds into the collapse, 425 milliseconds into the collapse. By the way, this gives you an estimate of the timescales of a core collapse. I mean, this thing is done in a second. It's really fast. You go from 6,000 kilometers to 50 kilometers in a second. It's nuts. Anyways, so this is one simulation on top. This is one simulation on bottom. All that changes between the top simulation and the bottom simulation is the neutrino in medium nucleon cross-section is changed by between 10 and 30%, which is a small change. And what that does is it changes a dud simulation into an explosion. Just looking at this last thing, this clearly looks like an explosion, and this is basically the matter falling back on itself. What this means is that if you want to understand why supernovas explode, you have to know the physics of the neutrinosphere to 10%, because changes to the properties of this stuff on the order of 10% can fundamentally change the qualitative outcome of a supernovae. And this is sort of the main motivation of why these lectures I'm giving you. Understanding the nuclear physics of the neutrinosphere is important. Okay, now we're going to see how do we solve this nuclear physics. We're going to do single neutrino, single nucleon scattering first in vacuum. Then we're going to see how does this work in medium, and then I'm finally going to do the in medium problem. Okay, so neutrinos can scatter off of nucleons in two different fashions. They can engage in what's called a neutral current reaction, or they can engage in something called a charge current reaction. Neutral current reactions happen through the exchange of a Z boson. Any flavor of neutrino bounces off of any flavor of nucleon through the exchange of a Z. So this happens inside the neutrinosphere. There's also charge current interactions. One second. Charge current interactions change the charge of the lepton. So an electron neutrino, for example, turns into an electron, and a neutron changes into a proton. So this is interesting. This changes the chemical composition of the stuff there. Muon neutrinos produce muons, tau neutrinos produce taus. Now, because the neutrinos in the neutrinosphere have energy of roughly 10 MeV, we know this from the Cameo-Condé data. We don't need to think about these interactions because a muon weighs 100 MeV and a tau weighs 1.7 GeV. There's not nearly enough energy to produce these guys. So the primary scattering processes that are happening inside of the neutrinosphere are neutral current reactions and this charge current reaction. Now, certainly, both of these processes happen in the matter. For the rest of the talk, I'm just going to talk about neutral current reactions. You can ask me at the end. This is for a technical reason. But we're just going to do this, but I just wish to say up front that both of these certainly happen. Okay, to capture the neutral current scattering process between neutrino and nucleons at low energy, it's helpful to use effective field theory techniques. So here's your typical effective field theory plot. Length goes up, so this is super microscopic physics down here, getting to larger and larger distance scales, more and more zoomed out. So at the standard model level, neutrinos scatter off of nucleons through interacting with quarks. Leptons interact with quarks by exchanging a Z or a W. And the nucleons, which are participating, are held together by the exchange of gluons, as you guys know because you're experts. But this is very complicated. And so in seeking a simple description of this problem, you can zoom out without losing much information. So first off, if you begin to zoom out at the electroweak scale, you can begin to forget about the weak bosons that participate in the interaction. So instead of keeping track of this propagator here, you can approximate the scattering between a lepton and a quark by a contact interaction. But at the electroweak scale, you still got gluons around. You're still zoomed in enough to disclose their presence. However, at the energy scales relevant in the neutrinosphere, you can use a tool, another effective field theory called pineless EFT. I'll justify this assertion in a few slides that pineless EFT works in the neutrinosphere. But this is at super low energy compared to the electroweak scale and the TeV scale. So at the pineless EFT level, the scattering between neutrinos and nucleons can again be approximated by a contact interaction. And furthermore, the nucleons are there rather than, say, quarks and gluons. And these nucleons scatter off each other through, again, contact interactions. So we're going to use this effective field theory to describe the neutrino-nucleon interaction. If you look it up, basically the neutral current scattering between a nucleon and a neutrino is given by a 4 Fermi interaction. Basically, there's a leptonic part, which is why this is called L, and there's a hadronic part in this J. This GF is close to 1 over the mass of the W squared. That comes from integrating out the W. Okay, so the leptonic current in the lingo of this game looks like this. You've got a neutrino coming in, a neutrino going out, and there's some gamma matrices in the middle. This is called an axial vector interaction. The hadronic current, J, is a little complicated. It has a 0th component and K components because it's a 4 vector. And it looks like this. This looks more complicated than it needs to be. Basically, what you need to know is that the 0th component of J looks like the nucleon density times the coefficient, plus again the nucleon density. This tau 3 in the middle is really unimportant. This just gives you the proton density minus the neutron density, again times a different coefficient. Okay, so J0 has densities, nucleon densities, and the K components of J have nucleon spins. We have n dagger, sigma K, that gives you spin, and this tau 3 once again just gives you a minus sign between protons and neutrons. So the upshot is, in the hadronic current, you have density operators and spin operators. And this is typically communicated as neutrinos scatter at low energy off nucleon density and nucleon spin. And from this, you can deduce this cross-section, which I flashed a few slides ago in our supernova estimate, that the low energy cross-section between neutrinos and neutrons looks like this. Okay, but now neutrino-nucleon scattering in vacuum is not what we need. We need to know how do neutrinos scatter in a medium of nucleons which are always interacting. And actually, to get this, it's not terribly complicated. Okay, I'm going to admit to you up front that what I'm about to show you, I completely stole from Alexei Voronin and Nikolina's book, Basics of Thermal Field Theory. It's I think, a really instructive book. But here's the idea. I've got some blob of matter. Okay, this is some blob of neutrinosphere. Happened to come out looking like a goldfish. I didn't mean it, but it looks like a goldfish. A neutrino comes in with momentum K, scatters through this stuff, comes out with momentum K prime. We would like to know the rate for the scattering process. What is the rate for a neutrino to scatter from momentum K to momentum K prime? Well, like any rate, you can compute it with Fermi's golden rule, which basically says that the differential scattering rate is given by a certain matrix element squared. I'll explain all these symbols right now. So this is basically the field theory version of Fermi's golden rule. So first off, TFI is the matrix element that is always in Fermi's golden rule. Basically, we have an initial state, which is scattered into a final state through some perturbation. This delta L is the delta L from last slide, leptonic current against hadronic current, and then it comes out in some final state. Okay, well, this initial state is what? It's some neutrino coming in with momentum K, and the system is in thermodynamic equilibrium. I forgot to say that. We're going to assume this system is in thermodynamic equilibrium. So that's state I is the ith eigenstate of the Hamiltonian. This is some crazy state which we could never possibly write down. It's a many-body state of a strongly interacting theory, okay? But we're assuming that the system began in state I, and it's going to go to state F, which is a neutrino with momentum K prime, and it's in some final state. Now, the pi's that are appearing in this sum is just a Boltzmann factor for being in equilibrium, okay? So if you stare at this Fermi's golden rule, what it says is the differential scattering rate is a bunch of matrix elements squared, that's Fermi's golden rule, weighted by Boltzmann factors. This comes from the fact that we're assuming it's in thermodynamic equilibrium. And you sum over all those initial states. We have some ignorance of its initial state, but we know the distribution of states. And then we're going to sum over all final states because all we're interested in is what is the scattering rate for the neutrino into momentum k. I don't care what the system is left in. I just want to know what's that rate. So that's where all these ingredients come from. By the way, V is the volume of the system. T is the time of observation. Now, because I'm trying to give an instructive talk. This next slide involves calculating this thing. Forgive me for putting too much math, but I think this is instructive. So how do you actually go about this? And I need this to justify, I want you to see something. So this matrix element, it's not that hard to calculate actually. Okay, well, it's an initial state, perturbation, final state. We saw that on the last slide. And if we begin to unpack this, well, the initial state is a tensor product of a neutrino with momentum k and the ith energy eigenstate of the system. This is what the perturbation looks like. It's an integral over space of a leptonic current against a hadronic current. And then the final state is k prime for the neutrino, and the system's left in some unknown final state. Now we're just moving this spatial integral out, and then you can do the neutrino part easily. If you contract this field against this state, you produce a spinor and a single particle wave function. And if you contract this neutrino against this state, you get a antiparticle spinor and again a momentum eigenstate wave function. However, what's left over is a matrix element of hadronic currents in some crazy state that you don't know. This is hard, and we're just going to leave this like this, okay? But my main upshot is that this matrix element looks like a space-time integral over some Fourier factor, a contraction of leptonic stuff, and a really hard thing to calculate. Okay, so you can sort of compartmentalize the difficulty, stuff it all into the hadronic thing. Okay, now I'm not going to keep going here. Basically, in order to get the differential scattering rate, we need to square this thing and average over p's and then take a limit. So I'm just going to wave my hands and tell you how this works. So basically, when we square this matrix element, we're going to have some nasty product of spinors. But this is just some function of k and k prime that has it'll have two indices at the end of the day when you square it. So the answer is going to have some yellow thing, which is I'll call L mu nu. It's a function of k and k prime, which carries all the neutrino scattering information. There's going to be a sum over this times its complex conjugate. There's going to be a weight. There's going to be a sum over i's weighted by Boltzmann factors. And then there's going to be a sum over final state. So that's going to give us a trace of a current-current correlator in a thermodynamic ensemble. Okay? I'm not writing it, but here's how we arrive at the answer. The differential scattering rate can be cleanly cleaved in two. There's a leptonic part, which comes from the traces over the neutrinos, and then a Fourier transform of a density-density correlator computed in a thermodynamic ensemble. Whoa, my Alexa just talked at me. I'm going to disconnect it. Jeff Bezos must be listening to this fancy physics. All right, so if you do this carefully and you actually, write out the leptonic currents and stuff, the scattering rate looks like this. This is the differential scattering rate for scattering into an angle theta and giving up an amount of energy Q0. It looks complicated, but basically these cosines come from this leptonic object. So does this prefactor. What really matters is that all the hadronic stuff lives in what are called structure factors. We have what's called a vector structure factor and an axial structure factor. The vector structure factor is a space-time Fourier transform of a density-density correlator. And the axial structure factor is a space-time Fourier transform of a spin-spin correlator. Remember, spin and density are appearing because these J's, as we saw 2 slides ago, are basically linear combinations of spin and density. That's why at the end of the day, these come out. So we've reduced the problem of, okay, you want to know the scattering rate of neutrinos inside the neutrinosphere because sensitive changes to this change the outcome of supernovae. The problem is reduced to computing these guys in a strongly interacting nuclear medium. It's not easy at all to do, but at least we have compartmentalized the difficulty into this object, compute these structure factors. Now, I'm going to show you a way to do this using the lattice field theory, but one more simplification matters along the way. And that simplification is that in this system, due to the specifics of the system, the neutrino scattering is roughly elastic, okay? So the neutrinos coming out of the neutrinosphere have roughly an energy of 10 MeV. We know this from the Kamiokande data. The nucleons have a temperature and therefore an energy of roughly 5 MeV. That makes them non-relativistic. And if you plug the numbers, what you find is that the scattering must be roughly elastic. Here's how you can see that. So imagine a neutrino comes in with energy Q and momentum Q. It's relativistic, so the energy and the momentum are the same. All right, we're going to do this by contradiction. We're going to say, okay, suppose that scattering is elastic, and then we're going to run into a contradiction, and we'll therefore conclude that the scattering cannot be elastic. Here's how you see that. So, okay, suppose that the energy transfer of the neutrino to the nucleon is roughly of the size of its momentum, which is 10 MeV. This is not a crazy estimate. It has 10 MeV to give up. Okay, well, if the neutrino gives up 10 MeV of energy to the nucleon, well, that means the change in the energy of the nucleon is 10 MeV. No surprise. Well, you can then deduce that if the energy of the nucleon changes by 10 MeV, then its momentum must change by an amount of 100 MeV. This just comes from solving this thing for P. Okay, so in order for the nucleon's energy to change by 10 MeV, its momentum must change by a lot more. It must change by 100, and that's because the nucleon mass is big. Well, if the nucleon momentum changes by 100 MeV, that had to come from somewhere. That had to come from the neutrino. This would imply that the neutrino gave up 100 MeV of momentum, which just can't happen because it started out with only 10 MeV of energy. This means that the energy transfer of a neutrino to a nucleon must be much smaller than its momentum, and this is what it means for a scattering process to be elastic. Now, this matters because what this allows us to do is to replace the dynamic structure factors. They're called dynamic because they involve energy transfer, which is time. It allows us to replace with good fidelity the dynamic structure factors by something called static structure factors. So the differential scattering rate into an angle theta for an elastic scattering process is given by this, where instead of dynamic objects with Q0, we have static objects where there's no Q0. So it's still the same form, though. It's just different objects appear. The static vector structure factor is a spatial Fourier transform of a density-density correlator. And the axial static structure factor is a spatial Fourier transform of a spin-spin correlator. I accidentally left a T here. Should not be here. This is equal time correlator. Okay. Now, what's important about this is that this can actually be computed from lattice field theory. The dynamic structure factor these days is basically beyond reach because of something called the sign problem, which I won't really get into. However, the static structure factors one can compute. And I'm going to spend the rest of the talk explaining to you how myself and my group have done this, okay? But I would just like to communicate that what we've just done is very typical in physics. We've taken a huge problem with a lot of moving parts, and we've slowly made a sequence of approximations to distill it into a tight, answerable question. If you want to know the scattering rate of neutrinos in the neutrinosphere, what you got to do is calculate these structure factors. I'm going to make one more approximation, again, for a technical reason. The data I'm prepared to show you today approximates the neutrinosphere as a pure neutron gas. This is a reasonable approximation. The neutrinosphere is 90% neutrons, 10% protons, but this is only made out of a necessity. Right now, doing protons is difficult. And in fact, we'll probably need to get the protons in the picture in order to have a final answer, because as we know, 10% changes to scattering rates can change the game. But what I'm prepared to show you is pure neutron gas calculations. Okay, sorry, it took me a long time to get to neutrons, but I wanted to explain what the heck we were doing. Okay, so what I'm going to show you how to do is how to compute static structure factors in a many-body medium, period. Because so we're going to use a tool called pineless effective field theory. This is an effective field theory of nuclear physics, which involves nucleon fields alone and contact interactions. And furthermore, I'm just going to leave out the protons and do pineless EFT of neutrons. It's a very simple theory. Because here the psi is a neutron field. It's got spin up neutrons, spin down neutrons. Because it's a non-relativistic system, the kinetic term looks like this. You may be unaccustomed to this, but the kinetic term looks like this. And then, like any effective field theory, the interactions are in a tower of interactions of higher and higher derivatives. So the leading order interaction looks like this. There's several next to leading order interactions, which involve two derivatives, and so forth. And the main thing that's important, excuse me, is that pionless effective field theory converges for momenta of the nucleon roughly less than a pion mass. This is because pions are left out. If you have a momenta on the order of a pion mass, you'll make pions. Now, if you ask, okay, at what temperature and what density will my momenta surely be less than a pion mass, you'll find that this will happen roughly for temperatures less than 10 MeV and for densities less than, say, 6% nuclear density. Comparing this to the neutrino decoupling region, this region, 10 MeV, 6% nuclear density, is actually the gray backdrop, which forms the background of the neutrino decoupling region. So the neutrino decoupling region lives squarely within the domain of convergence of pionless EFT, and this is why we are choosing this for this problem. It's the simplest possible EFT that can get the job done. Now, what I'll show you today gives just the results of the leading order theory. This is already a hard enough problem. So we've got no C2 operators in here, if you know what that means. So basically, this is our theory, okay? Kinetic term, 4 Fermi interaction. Now, there's two main challenges that get in the way of computing what you want here. Ostensibly, you look at this and you say, how hard can this be? Let me tell you. What we want is basically observables in a thermodynamic ensemble. We want density-density correlators and spin-spin correlators. Two things make this really hard. First off, this is nuclear physics, so the couplings are huge. In particular, the neutron-neutron scattering length is negative 18.9 Fermi. That's enormous compared to nuclear physics scales, which are like a Fermi. What this means is that even if you do a two-particle scattering process, forget many body, two particles, in order to actually compute the scattering amplitude for this theory, you have to sum up an infinite number of diagrams. These loops are not suppressed. All of these diagrams have the same size. All right, so if you want to do two particles, you have to sum an infinite number of diagrams. If you want to do many particles, not only do you have to compute this infinity of diagrams, you have to compute another infinity of diagrams. The finite density of the neutrinosphere introduces more large scales that you have to deal with. So, for example, if your goal is to compute a density-density correlator, say to do this vector structure factor, diagrammatically, one has to compute these things. These labeled circles are X and Y. So you've got a leading order loop, you've got a loop with one interaction, more interactions. The problem is, again, just like this, all of these guys have the same size. And so if you want to compute the density-density correlator, you have to compute the stuff of nightmares. And so what this means is that diagrammatic methods are really not a good way to solve this problem. You have to do a lot of work and solve an infinite number of diagrams to get started. And so that's why I'm going to use a different tool to solve the system. I'm going to use lattice field theory. Now, lattice field theory takes a while to explain. I'm just going to give you the rough outline of what this tool is and how to use it. Okay, it's a different way to do quantum field theory. What we want are observables in the thermodynamic ensemble. Okay, neutrinosphere gas, density-density spin-spin correlator. Lattice field theory is a way to do this, which comes in a couple of steps. Basically, you compute the path integral is the punchline. Straight up compute the path integral. The way that you get there is through a couple of steps. The first thing that you do is discretize space. Okay, so if you take the Lagrangian of the theory, convert it into a Hamiltonian, and then say, all right, I'm going to approximate space as a lattice with lattice spacing delta x. Here's the Hamiltonian you arrive at. Also, this is a way to regulate the theory in the UV. This is literally equivalent, by the way, to taking a cutoff regulator, if that's your favorite regulator, where you choose a qubit cutoff in momentum space. They're literally equivalent things. So what I'm trying to communicate is this may not be as foreign to you as you think. If you're used to cutoff regulators, you're used to lattice field theory. So this regulates the theory in the UV, makes it finite, and it allows us to begin computing things. So the second step is to discretize time. And by time in this sense, I mean the temperature direction. But I don't want to be mystical about it. What I mean is this. I want, say, the partition function. I can approximate this partition function by trotterizing it. I can take this operator and divide it into parts, into the kinetic energy part and the part which involves interaction. Delta t here is basically you take beta and you cut it into a number of time slices. Delta t is the beta per time slice, okay? If you do this trotterization, what you find is that this approximate operator converges to the operator that you want at a rate of delta t squared, where again, delta t is beta over the number of time slices. So one wants to do this because this is easier to compute than this, okay? So now we've discretized space, we've discretized time. I have some theory that has space-time discretized. Now, this next step, I can't really show you because it's really complicated, but I can just tell you that this works. The next step is to introduce what are called auxiliary fields. That amounts to taking this potential term, this is the 4 Fermi interaction, and decoupling it through something called the Hubbard-Stratanovich transformation. This basically allows you to write a 4 Fermi operator as an integral of a bunch of 2 Fermi operators at the cost of introducing an auxiliary field that I'll call A. Okay, so now we're starting to look like path integrals. This operator in Hilbert space now is beginning to look like, okay, integrate a bunch of fields. I'm skipping a lot of steps, but I still hope it's clear. So now we arrive basically at the last step. Okay, you can decompose the numerator and the denominator of what you want into a bunch of path integrals, which are really hard to calculate. And this approximate object converges to the desired object at a rate delta t squared. So all you got to do is take a time continuum limit, and then you converge to the exact result of the discretized theory. And then you can take a spatial continuum limit and converge to the continuum results. All you got to do is just compute the whole path integral. Now, that's hard, obviously. The way that we do this in practice is through what are called Monte Carlo methods. So basically what you do is, okay, your task is to compute this thing. How the heck are you going to do that? Well, you stare really hard, and I wish that this laser like stayed, because I'm trying to highlight, there's actually a probability distribution hiding in here. It's right here. Can you see me circling it? So this object P of A, which is, basically the action living upstairs divided by the integral of the action downstairs, is a probability distribution. If you're lucky enough that this is a positive definite function, and I'll just tell you that for the neutron gas, this is a positive definite function. So the way that you compute the path integral is you use fancy numerical methods, which I won't describe, to sample fields A according to this distribution. You sample according to the distribution and you put these fields in your pocket, okay? You collect a large number of them, say 1,000 or 10,000 if you've really got a lot of computer time. And then you can approximate the object that you want by simply averaging over the collected fields. I forgot a 1 over n here. You don't sum, you average. And what you are guaranteed is that the stochastic estimate of the path integral converges to the desired object at a rate of 1 over the square root of n. Okay, so you take a lot of samples of the probability distribution, and the more samples you take, the closer you get. So that's the whole game. Okay, this is how you do the many-body physics of pineless EFT without approximation, is compute this thing. Now, it's not easy to do, and I'm not going to belabor this because whatever, but, it takes supercomputers to do this. Here, we use 2 of them, one in the States, one in Germany, and all the fancy methods for lattice QCD. So yeah, if you've ever heard a talk about lattice QCD, what I just described to you is not strictly speaking lattice QCD. They're both lattice field theories, but they're different Lagrangians, if you will. However, because the lattice QCD community has existed for a really long time, you can just port over all of the goodness that community has developed over time. And this is what we're enumerating here. We use a method called hybrid Monte Carlo, things called pseudo-fermions and stuff like that to make these simulations possible. Okay, now in my last few minutes, I'm sorry that I've sort of come to the results only at the end, but let me show you that this whole idea works. You can compute the many-body physics of the neutrinosphere exactly. So first off, we'll do thermodynamics. So what I'm showing you are actually, for this system, the first calculations of the full continuum infinite volume limit thermodynamics of this system. Okay, over here we've got the equation of state. Over here we have something called the tan contact parameter. Basically, the equation of state is what's the density as a function of mu. The variable on the x-axis is actually the fugacity z, which is the exponential of beta mu, but you can think of this axis as mu. As you dial up mu, the density gets bigger. These red points are full continuum infinite volume limit extrapolations of lattice calculations. And the gray band, or the gray curve, is something called the virial expansion. This is a exact result at low density and begins to be not true at high density. So any calculation must converge to the virial expansion at low density. And indeed we do. This is just to prove that what we're doing is not crazy. It reproduces the virial expansion, and we have every reason to believe that what we're doing are the exact results for pineless EFT. The tan contact is another thermodynamic observable, which I will elaborate on in a slide or two. Basically, I'm just showing you this to show you that we are in the ballpark of a bunch of other calculations. Okay, here are the all-important structure factors. These are the things I've been spending 2 lectures building up to this. Here we are. So here we have the structure factors, the axial, the vector, that's the density in blue, and the axial, which is the spin in red, for 2 sets of thermodynamic conditions. So basically what myself and my group have done is to choose 2 points in density and to show that this can be done, that you can indeed get the exact results for a pineless EFT in a many-body system for the structure factors. So we have a temperature of 4.14 MeV, that's squarely within the neutrino decoupling region. And we're simulating at about 3 and 5% of nuclear density. So 3% nuclear density is on the edge of the neutrino decoupling region. 5 is a little bit denser than the neutrino decoupling region, but our goal was to just show that we can certainly get beyond the neutrino decoupling region. And now our next task is to march inward and to cover this whole phase diagram, or cover this thermodynamic space. This isn't a phase diagram. This is just 2 axes. Anyways, good. Okay. So this top plot, there's a lot of information here. This top plot is 3% nuclear density, and this bottom plot is 5% nuclear density. The vertical axis is the structure factor. These are the Fourier transform of the correlators as a function of the momentum Q of the Fourier transform. Okay, so you need to know a range of Q in order to account for all the possible scattering processes. This dotted line is the free field theory results, and the lattice results are in blue and red. So the first thing which sticks out is that actually there's quite a bit of a difference between the free field theory and the interacting theory. At say low momentum, the differences are between 30 and 50%. This is well into the domain that's needed to fundamentally alter the outcome of a supernova. We needed 10 to 30% to change a Dud into an explosion. The interaction effects can already produce well beyond what is needed. Okay, so I think this proves that we really need to solve this system in order to understand supernovae. Same holds at 3% nuclear density, at 5% nuclear density. At low Q, at least, there are changes on the order of 30 to 50%. There are big differences between the free theory and the interacting theory. Now, there's some cool sanity checks that we performed on this because, this is, you don't know a priori if what you're getting is right. We have reason to believe our thermodynamics is coming out right and our extrapolations appear under control, but there are additional checks that we perform to give us confidence that this is the real result. One is a prediction from the operator product expansion. It's basically, if you've never heard of it, the operator product expansion is a way to expand operators in the Hilbert space and understand the short distance behavior of correlation functions. And the operator product expansion computed by these guys here shows that the vector structure factor, for example, it needs to converge to the density at high momentum, and it does so at a rate of 1 over Q, where the coefficient of Q is the tan contact from 2 slides ago divided by 8 times the volume of the box. Similar for the axial structure factor, there's just a sign difference. So what these bands are an independent calculation of the tan contact, and we're just plotting this prediction of the OPE. And you can see that the lattice results converge at a rate predicted by, I'm running at the edge of my voice, at a rate dictated by the operator product expansion. So this gives us confidence that what we have indeed is correct. There's also, so that's at high Q. At low Q, there are relations between the structure factors and thermodynamic functions, which are given here, basically. At low Q, the vector structure factors ought to converge to the derivative of the density with respect to mu, and the axial to the derivative of the spin with respect to h. I was silly and I totally forgot to put those lines here, but we find agreement between the low energy these fluctuation relations at low q. Okay, so this brings me to the conclusion of my two-part series. So basically, I wanted to tell you a bit about core collapse supernovae. I wanted to convince you that the neutrinosphere is an important part of the problem. And in order to understand what's going on in the neutrinosphere, we need to calculate the structure factors of nuclear matter. I just presented to you the leading order structure factors for the neutron gas. What remains in order to really get this system down is twofold. Protons need to be included. They compose 10% of the system. We need to know the system to 10%. And what needs to be checked too are how robust are these leading order results? Do the next leading order operators correct the heck out of these results, or are they just small corrections? The expectation is that the NLO operators are small and won't change the story much, but we are running these calculations now. And I hope to tell you what we find when we find it. With that, though, I'll thank you for your time. I really appreciate your attention. And I think I went over time.
Okay, super. Well, we are always very, very jealous of time. So any extra time that you give us is very much appreciated. So let's maybe open the floor for questions first in the room and then online if there are questions online. Yeah, Dave, please go ahead.
I have two, but I'll save one for later. So the first one is a lot of the approximations like the pilus, EFT, and all those required certain energies on the neutrino. And you said that we are getting this data from Kamiokande. Is there an estimation on how much energy is lost between the supernova and us detecting it on Earth? Is it completely negligible, or what's
roughly speaking?
Is it completely negligible? Okay.
Can I ask you guys a quick question? So when I by the way, I've exited full screen because I couldn't see anybody when I was in full screen. And when I exited full screen, I had this box that said, "Would you like the meeting to be recorded?" Was that box there the whole talk? Were my slides obscured the whole time?
No, it's looked great. It looked perfect for us.
Okay, whew, thank God. Okay, all right, keep them coming.
You know, we have no problem telling people to have something in their teeth or if there's a box in their slides.
Excellent, excellent.
Would you like to ask your second question?
Well, I guess a sort of a follow-on. If the neutrinos were, say, for instance, higher energy, would the procedure sort of be the same, but we just have to pick a different EFT, or would it fundamentally break something else?
So actually, it's not too bad that the neutrinos could be higher energy. Let me just go to the slide. The neutrinos could be higher energy, and it wouldn't pose much of a problem. The main I'm also in this view because I want to be able to see you. These neutrinos could get to quite a bit higher energy before they resolve the substructure of the nucleon. What made pineless EFT the choice was not the neutrino energy, but actually the nucleon energies. It's the fact that the nucleons have roughly 5 MeV of energy and densities low enough that they're slow, that made pineless EFT the choice. If the neutrino, so if you go inward from the neutrinosphere towards the center of the star, the temperatures get higher and the densities get higher too. And then pineless EFT ceases to be a good description of the nuclear matter there, and that's why I can't calculate there.
Okay. I guess the second question, which I think I'm going to know the answer to, is you mentioned 90% neutrons, 10% protons. You haven't accounted for protons. Is the electron cross-section also just unimaginably tiny and we don't care about it?
I'm so happy you asked that question because I wanted to talk about it, but I also overloaded things. It's not unimaginably small. It's just a factor of, here, I'll show you. Can you see this?
Yes.
So, okay, so here is the low energy electron neutrino electron neutral current cross-section. There's two things that make it smaller, although not unimaginably small. First off, oh, and by the way, this is for comparison below. This is the neutron one. So the prefactor, all right, these are the same, roughly speaking. One's got a 10 to the minus 49, that's the electrons, and one's got a 10 to the minus 48, that's the nucleon. So already the electrons are 10 times smaller cross-section. On top of that, the nucleon goes like the energy squared, and the electron goes linear in the energy. So if you plug in 10 MeV, that's another factor of 10. So that comes out to the electron cross-section is about 100 times smaller. So if eventually we find that we got to know the system to 1%, well, first off, God help us. Second off, okay, then we'll do the electrons, but it's like a 1% effect.
Okay, okay. Does it also have to do with the number of electrons that are actually sitting in the neutrinosphere? That is mostly neutron.
Yeah. So exactly. So there's a couple of things not helping the electrons. First off, their cross sections are 100 times smaller. Second off, there's 10 times fewer electrons than neutrons. There's another factor of 10.
Okay, yeah, 21 accuracy.
Yeah. Good. Yeah, cool.
Yeah, that was very interesting. I'm curious, is there certain like experimental observables that you guys would be aiming towards predicting, or is like how do you actually make contact with the experiment? Because I mean, I guess astronomy observables are a bit more tricky than it is with, say, particle physics. Yeah, that's what
Yeah, that's fair. So most of the experimental observables that I expect to make contact with are actually simulations. So from Earth, when we it really stinks. Like supernova 1987A happened in 1987, and 50 years has passed, and we haven't seen another one since then. So we're still gathering information from supernova 1987A. Like it's grown quite large since then, but actually, I make a bit more contact with the simulation community. So like that's where these numbers get the numbers that I gave you, this curve for the structure factors, get input into there. And I mean, the first question is, okay, does modifying the description of neutrons make an explosion happen? That's the very first coarse grain question that I want to know. That I would make contact with the community. And then once there's a yes, no question to that, it's like, okay, do these curves fundamentally alter the electron fraction that comes out? The electron fraction is really important because, as we learned in the last lecture, they exert a lot of pressure because they're really light. And so it's things like that in simulations that this work would come into contact with.
Thanks. Super. Other questions in person or online?
Well, let me throw one in, just for the heck of it. You were mentioning that in your effective field theory, then the next order contributions are small. Is this simply power counting? Are the powers so big that they put it away, or is there another reason for that?
It's just power counting, and I should say we don't. So what is true? I'm going to zoom out just so you can see. So actually, let me go back. Okay, so the leading order, if you look in the two-body sector, for example, you can do the leading order theory. In the two-body sector, you have to sum an infinite number of diagrams, and you get an amplitude of a certain size. A consistent power counting scheme involves perturbative insertions of the next leading order operator while doing the fully resummed C0. It's an annoying technicality of low energy nuclear physics. However, if you do that procedure, one, you find that the theory remains renormalizable, and second, that the next to leading order insertions are, say, a 10% effect.
Mm-hmm.
So what is known is what happens in the two-body sector. We don't actually know if these effects will remain small in the many-body sector, and this is a part of the reason why we're doing these calculations. We have an expectation it'll be okay based on the two-body argument, but we don't know yet.
Mm-hmm. Okay. Very good. Thank you.
So I wanted to, actually, this is a good slide to be on. I don't have a incredibly solid understanding of lattice QCD, but there's always this comment about when you go to finite density there, you hit the sign problem again in lattice QCD. And you're somehow managing to avoid the sign problem when you're at finite density in this theory. So to a lay person, can you give a nice sort of finger feel for why that happens?
Sure, absolutely. Actually, thank you. Like, this is a technical point I wanted to skip to concentrate on the physics, but this is actually another main reason of why we're doing this funky lattice field theory, putting pineless EFT on the lattice. Because if you try to do it with QCD, you have the sign problem and you can't do it. So this is one reason to launch over to just starting with a different theory and putting it on the lattice. Okay, why is there no sign problem for neutrons? I wish I could give you a physics argument, but okay, I can say sort of a technical reason. So, okay, in the whole procedure, actually, let me go down here. In the procedure of going from the Hilbert space thing that you really want to, okay, here's my computational method for doing it. You run into something called the fermion determinant. That's what this det D is, okay? And the det D, which appears in lattice QCD, and the det D, which appears in pineless EFT, are different determinants because you started with different theories. In pineless EFT, which is a simpler theory than QCD, it has a very simple structure. It's block diagonal in spin space. So there's like an upper left corner, which encodes the spin up neutrons, and a bottom right corner, which encodes the spin down neutrons. And they are exactly the same. And so when you take a determinant of this 2x2 block matrix, what you actually run into is the square of something. And because you run into the square of something, this det D is positive, and that's why there's no sign problem for pure neutron matter. Conversely, in lattice QCD, the det D which appears involves just, again, a block diagonal matrix, but the two blocks are not equal to each other. And so when they are, and moreover, they're complex. And so when they're multiplied together, they can remain complex. That was a very mathy answer to your question, but I fear that is the best that I can do.
No, I think that's good. So somehow, for reasons that are technical, the determinant you have here is a real determinant and ends up being a determinant squared, which is positive definite. Whereas in QCD, it's some complex determinant, and then you get phases, and then it's very, very bad.
Exactly. Actually, let me elaborate one more thing. So I said very quickly early on in the talk, oh, I'm going to drop protons for a technical reason. If you include protons, this 2x2 block thing becomes a 4x4 block thing because your nucleon field has 4 components. And the sign problem comes back when you add protons to the problem. So basically, like, you have two parts of the block for protons, 2 parts of the block for neutrons, but they're different matrices because protons and neutrons have different coupling constants. And so actually, the reason why we haven't included protons yet is because we do, again, run into the sign problem. So this is a really annoying technical thing that we're still trying to figure out to include protons. So, we're not totally out of the woods.
Yeah, it seems like, to me, I'm not quite sure how to say it, but because you're working, it seems like, at quite a high density. You made this comment before that the density is actually quite large. If you do have a sign problem and you include protons, that seems like a fundamental stumbling block or fundamental challenge that it doesn't seem like it seems like you'll have to invent something really new and really different to overcome that.
Something like this, perhaps. Okay, so I let me admit up front that I don't know if this is going to work, but because of the prevalence of sign problems in lattice field theory, basically what I spent my entire PhD doing, along with a bunch of people, was developing a general method for taming sign problems. I mean, the sign problem prevents you from doing lattice QCD at finite density. It prevents you from including protons in this very specialized problem I just told you. It prevents you from doing any real-time dynamics at all on the lattice, which is really irritating. So I will explain this quickly. If you want me to explain more, happy to. But basically, here's the thing. When you do a lattice field theory calculation, you're basically doing a giant integral over some manifold. To take a simple example, if you do like 5-4 theory on the lattice, you're integrating over Rn, like the real numbers to the nth power, okay? What's really cool and a new thing is that you can do contour deformations to path integrals, just like how you can do contour deformations to one-dimensional integrals in complex analysis. So we use this all the time in field theory. Okay, I've got an integral along the real line. That's way too hard. Let me deform my integral to an arc at infinity, pick up a residue, blah, blah, blah. Okay? You can do the same thing with path integrals. Somebody hands you a path integral with a given integration manifold. You can actually change that integration manifold for basically any lattice field theory, and it doesn't change the answers because Cauchy's theorem, which is like what's at play in one dimension, actually generalizes to many dimensions. And every lattice field theory ever is a many-dimensional integral. So we have been using this fact that you can use Cauchy's theorem on path integrals to tame sign problems. I'm happy to tell you more, but basically what you can do is there are now well-developed ways to take a manifold with a bad sign problem and to deform that manifold to some crazy manifold in high-dimensional complex space with much gentler sign problems. And we've been slowly working up from like toy systems to bigger and bigger systems. So at this point, we've been working on this technique for about 5 years. We can take 2+1 dimensional systems with really bad sign problems and basically get rid of it. So this is not lattice QCD at finite density. This is not, 1,000 nucleons, but we are slowly trying to march towards these problems. And we now have this tool, albeit who knows if it'll work yet.
All right, super. That's really, really interesting. Maybe just a final possible follow-up question, which is perhaps not particularly well formed, but I know that so if you look at analytic continuation in one dimension and through contour integration as you motivated is thinking about the analytic continuation of a function, that's when when you do this in undergrad, it's a function of one variable. But when you analytically continue a function of many variables, it gets things get subtle very quickly, and there's these like edge of the wedge theorems. And I'm wondering if any of it is at play when you're doing an infinite dimensional analytic continuation.
Okay, totally good question. Let me say first though that this is a finite dimensional analytic continuation, and that really matters. So like, I'm not trying to deform a continuous path integral that involves math beyond my pay grade. These are just lattice path integrals with finite number of dimensions. First. Second, this edge of the wedge stuff you're talking about is definitely something that you have to worry about. And the successful contour deformations, the ones which actually work, I would say there's like 2 classes of good contour deformations. They are specifically designed to never cross a forbidden wedge, to put it succinctly. So these deformations are designed to respect the constraints of analytic continuation. It's not easy to do, but it's definitely a part of the calculus.
Yeah, I feel like visualizing this would be non-trivial.
Super hard. Yeah, I know I have to make cartoons like this, which like are just like laughably.
Super. Okay, so thank you very much for having the patience to go through those questions from me.
Sure.
Any last questions from anybody online or in the room? Doesn't look like it. Super. Well, let's thank our speaker one last time.
Thanks a lot. That was good fun.
Thanks. I appreciate you coming, Herbert. It was nice to meet you. You too, Frederick. You too, Macy. I hope I didn't butcher that.
Maciek and Mwande.
Maciek. Okay. Oh, Mwande is here. Oh, hey, cool. Excellent. All right, friends. Thanks for your time. Yeah, this was great. Thank you.
You're welcome.
Thank you, Neill.